We learned early on that gravity is what makes things fall down. Sir Isaac Newton, a brilliant mind, gave us the law of universal gravitation. It explained why planets orbit stars and why the apple falls from the tree. Newton's theory described gravity as a force acting across vast distances. This force depends on two things: mass and distance. More massive objects exert a stronger gravitational pull. This is why Earth, a massive planet, keeps us grounded. The farther apart objects are, the weaker the gravitational attraction between them. Newton's picture of gravity worked remarkably well for centuries, explaining the motions of planets and moons with impressive accuracy. It allowed us to understand tides, predict eclipses, and even launch rockets into space. For everyday life, Newton's laws are still incredibly useful. As successful as Newton's theory was, cracks began to appear in the 20th century. Scientists observed phenomena that Newton's theory couldn't quite explain. The orbit of Mercury, the closest planet to the Sun, exhibited a slight wobble that didn't fit Newton's equations. Moreover, Newton's theory treated gravity as an instantaneous force, acting across the vastness of space without any delay. But what about the speed of light, the cosmic speed limit? How could gravity act faster than light could travel? These inconsistencies hinted at a deeper, more fundamental theory of gravity waiting to be discovered. Enter Albert Einstein, a revolutionary thinker who forever changed our understanding of gravity. Einstein proposed that gravity is not a force acting across space but rather a consequence of the shape of space-time itself. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip, a curvature in the sheet. This is akin to how massive objects like stars and planets warp the fabric of space-time. Einstein showed that objects moving through this warped space-time follow curved paths, much like marbles rolling around the bowling ball's depression. This curvature is what we experience as gravity. Einstein's theory, known as general relativity, provided a more complete and elegant explanation for the universe's gravitational dance. It explained Mercury's orbital anomaly and predicted the bending of starlight around massive objects, a phenomenon later confirmed by observations. While the rubber sheet analogy is helpful for visualizing warped spacetime, it has its limitations. It only depicts space as a two-dimensional surface, while in reality, we live in a three-dimensional universe. The analogy also fails to incorporate time, an integral part of Einstein's theory. To truly grasp general relativity, we need a more comprehensive visualization, one that encompasses both space and time. Imagine a loaf of bread, representing space-time, with each slice representing a snapshot in time. Now, imagine a heavy object placed on the loaf. It not only creates a dent in the current slice, but also distorts the slices above and below it, representing the curvature of space-time across time. This imagery helps us understand that gravity is not just about spatial curvature but also temporal curvature. Time itself flows differently in stronger gravitational fields. This has profound implications such as the time dilation predicted by Einstein's theory and confirmed by experiments.